It's a pleasure to watch how these three-phase windings are getting fabricated in the factories. What you see here is a fully automatic winding process. The windings take in electric current and create a rotating magnet field out of it. This RMF is responsible for the motor's rotation. You might be curious about how this magnetic field rotates even when the windings are stationary. Let's unveil its working. Come along. The winding design is not so obvious. It is clear from these visuals. Engineers reached this winding design with years of effort with design iterations, analysis, and the use of fundamentals of electric engineering. So let's start with the fundamentals, and we will reach this design towards the end of this video. Before starting a winding design, we should first understand the qualities of a good RMF. An RMF should have a smooth shape, as shown. It should not get distorted during its rotation. And third, the central flux lines should be perfectly radial. Let's start the design journey to achieve this perfect RMF using a simple coil. When an alternating current is passed through a coil, the magnetic flux will fluctuate as shown. Now, let's add two more coils which are apart by 120 degrees. Here, each coil produces its own magnetic field, fluctuating in nature. When we add these magnetic fields, we get the combined magnetic field as shown. This design is a failure. The magnetic field is not rotating. This is where one of the godfathers of electrical engineering, Nikola Tesla, comes into picture. He observed this disappointing behavior of magnetic field's fluctuation. This field fluctuation happens because all the three fields, maximum or minimum, happen at the same instance. Tesla, while walking in a park brainstorming ideas to create rotating magnetic fields, wondered what if he keeps maximum values at these three fields at different instances? Then there will be no instant when all three currents are zero or maximum at the same time. Eventually, the resultant field will not become zero at any instant. In short, he can avoid the fluctuating behavior. Using the phase shift concept of Nikola Tesla, let's develop a winding which can generate a rotating magnetic field. At the instance to time zero, the resultant of these individual magnetic fields is as shown. Let's save this position for future reference. With variations in AC currents, the magnetic fields take different orientations. If you compare these three instances, you can see that it is like a magnetic field of uniform strength rotating. This winding arrangement is a 6-slot design and generates two-pole rotating magnetic fields. There you have it. We have just made the magnetic field rotate with stationary coils. Here, we used a single turn for the winding. However, in the industries they use hundreds of thin cable turns. This will obviously increase the magnetic flux strength. Each of these turns is insulated from the other turns with the help of a liquid varnish lamination. However, the story is not over yet for the winding design. These windings are generally supported inside an iron structure, which also carries the magnetic flux lines. To check the quality of the RMF, we have to rely on FEA results produced with the help of EMWorks 2D software by SolidWorks. You can see that this RMF has two poles, but the central flux lines are not radial to the rotor. You can also see that during the rotation of the RMF, the shape is not consistent. This non-uniformity arises because of the huge gap between adjacent conductors. So, to achieve the first criterion, a more uniform shape during the rotation, we have to increase the number of conductors adjacent to each other. Let's make it 12 this time. The winding of this 12 slots design is made by connecting one more coil in series with each phase coil. Here, observe the current direction. Well, this straightforward connection won't produce a two-pole magnetic field. Let's overlap this pair of coils. What you get is a two-pole field. Perfect. Now, let's do the same for the other two phases. If you combine all three of these coils around a circle, the left sides of these coils carry current in one direction, and right sides carry current in another direction. This gives the resultant magnetic field as shown here. This beautiful winding produces a two-pole RMF with better shape and uniformity. It is clear from this FEA result. This winding is able to keep a uniform shape throughout its rotation. Interestingly, just by doing a few more modifications in this winding, we can get a four-pole RMF. If you remove the overlap we did earlier in the coils, we can get the four-pole RMF very easily. Here, each conductor of the R phase creates individual poles. Thus, all three of the phases combined create a four-pole rotating magnetic field. Let's arrange this design also in a circular core. Apart from the difference in number of poles, can you predict any other difference in these rotating magnetic fields? The speed at which both the RMF are rotating is different. This is because the N pole of a two-pole RMF reaches 180 degrees after a half cycle of sinusoidal current wave. However, in the four-pole winding, the N pole reaches just 90 degrees. Thus, the two-pole RMF has double the speed to that of four-pole RMF. Eventually, the two-pole winding gives more speed, yet lesser torque, and the exact opposite is the case with four-pole winding RMF. As you go on increasing the poles, the relation of speed and torque stays the same. For an even better and smoother experience of rotating magnetic field, a 24 slots winding is preferred. These slots are nearer and uniformly placed over the stator periphery. So here you can see the rotating magnetic field, how it rotates uniformly, having constant strength of magnetic field throughout its rotation. From this, we made the conclusion that as we increase the number of slots, the more uniform and constant strength rotating magnetic field we achieve. This is the beauty of windings. Here you can see the more complex windings wound on the stator. These winding types are selected according to the applications you want to use the motor in. In the factories, these coils are wound on a pharma. At a time, 2 to 3 sets are wound on each side. This pharma loaded with coil groups is inserted into the stator core by hydraulic pressure. Then comes the human intervention to make precise connections between these coils. Then the windings are tested and sent to operate your mixer grinder, washing machine, or your air compressor. We hope you have enjoyed the video. We will see you next time. Thank you.